Hello, everyone. I welcome you all for taking out your time and attending my PhD exit seminar. My name is Suyash Gupta, and I really hope you know my name, otherwise you're in a wrong presentation. And today I'll be presenting a snapshot of my thesis, which is titled Resilient Scalable Architecture for Permission Blockchain Fabrics. This work I did at Explorer Systems Lab, University of California, Davis. So what is this work all about? To understand this work, we'll take two folks like Alice and Bob and a bank. Alice and Bob are like you and I. They also work, and whatever the money they get, they place it as savings in the bank. Now bank stores the money for them. Now Alice wants to buy a house. So what does she do? She takes a loan from the bank. And now she uses this loan to actually buy the house. Now, coronavirus happens. As a result, Alice loses her job. Now this impacts Alice because she misses her loan payments. And now what the bank can do is that bank can actually block all of her savings. And this affects Alice because she's not able to have a control over her money. So how could this all happen? That's the important point. First, there's centralization because bank has the control over all the money. Bank has the monopoly because Alice and Bob are using bank to store their money and they cannot do anything more about it. They do not have control and their voice does not have any value in this system. So the main aim of this presentation is how can we solve this type of problems? First, a statutory warrant. This presentation is just too good. It will change your life. I'm just kidding. So let's get back to the solution. What is the solution for our problem? To understand the solution for this problem, let's try to understand what are the type of properties that we want. First, we want decentralization. We do not want one single person's control. We want democracy. Everyone should have some sort of right. We want control of data, and we want everyone to have a right to vote. So how can we achieve these problems? First, what do we mean by decentralization? Well, when we say decentralization, we want to talk about a network where Alice, Bob, bank, and everyone has an equal role and can play the same game. And then when we say about democracy, we want to give everyone a right to vote. Basically, for every transaction, everyone can send a vote and decide whether they want to approve this transaction or not. Now, what else do we want? Now that we have decentralization democracy, we want to basically run something to ensure the transaction gets done. And the first step to do in this direction is to try something called as commit protocols. These commit protocols work on something called as partition databases. When we say partition databases, what we want to say is that every node in the system is holding its own copy of data. And traditionally, these partition databases or these commit protocols have two variants. The first variant is basically the two-phase commit protocol, where all the nodes work in two phases and they reach a decision. But traditionally, it has been shown that this protocol is blocking. As soon as there is any failure, this protocol stops working. So the next variant is to use three-phase commit protocol. Now, three-phase commit call works well. It is able to avoid the node failure, but as the name says, there's an extra phase which makes it expensive. So our first solution in this direction was to design what we call as easy commit protocol. And this easy commit protocol basically requires two phases, like the two-phase commit protocol, and is non-blocking. And how does it work? Well, it builds on a principle, what we call as first transmit and then commit. And this easy commit protocol, we published in EDBD 2018. But we realized that when we were building easy commit protocol, and then we saw two-phase commit protocol and three-phase commit protocol, what we saw is that these protocols cannot be applied to wide area networks because there's a lot of latency in wide area networks. So to solve that, we designed what we call as geoscale easy commit protocol, and that we published in Journal of Distributed Parallel Databases. But are we done? Is this all? Not exactly, because commit protocols only support node failures. What happens if there is a message loss in the system? What happens if their messages are getting delayed? What happens if network breaks down? In that case, we need something more. And worse, what if there are some people who are Byzantine? For example, Bob can act malicious. The bank may stop responding at all. So we need a system which can handle all these problems. Just the commit protocols are not sufficient for that scenario. So to reach such a system, first, we move toward the design of replicate databases instead of partition databases. And when I say replicate databases, I mean that every node has exactly the same data. Then we said that there will be voting round, but there should be some rules for the voting. And those rules we define as consensus. And those rules are as follows. Every replica should vote only once. Each vote should be counted only once. Winner is the person who gets majority of votes. And we should ensure there's only one winner. Now, another thing that we require is that, so we have the voting defined, we have the replicate databases, but we need some sort of way to handle the Byzantine and malicious nodes. So for that, we use Byzantine fault-tolerant consensus. And why Byzantine fault-tolerant consensus? Because prior works have shown that it is secure and it allows authentication. So what do we expect from this Byzantine fault-tolerant consensus? The first thing we expect from this consensus is that all the replicas should have the same state. They should have exactly the same data. And second thing we expect is that if client is sending its transaction should be processed. The system should be live. So these are sort of minimal expectations that we expect from this Byzantine fault-tolerant protocol. Further, we have a replicate system, we have a consensus. Now we need to log everything. And for that, what we use is an immutable ledger, which we call as blockchain. A blockchain is nothing else but a linked list of blocks, where each block includes the hash of previous block, and each block includes a set of client transactions. So now we have all the tools ready. So let's try to get into some applications. So where is this Byzantine fault-tolerant consensus applied and where is this blockchain being used? Well, if I ask you the applications, the simple applications we'll talk about is Bitcoin, Ethereum, all the famous cryptocurrencies. But do you know there are many more applications? This blockchain and this consensus being applied in healthcare, waste management, and so on. But still, as soon as we talk about blockchain, everyone says cryptocurrency. Why is that the case? Why just cryptocurrency? The first thing is that all of these existing blockchain applications, especially those cryptocurrencies, have quite low throughput, like 10 transactions per second. And you could require extreme energy consumption. Further, their design is based on something which is called as reward-based model. Basically, every participant, if he has to work honestly, we have to give him some incentives to work for. And finally, the identities of all the participants should be known a priori. Now, with such a model in place, these systems suffer what is called as fork. Basically, at some point in time, the blockchain might split into multiple chains. So how do we actually solve this problem? And that is the main focus of my research and this presentation is that we want to make Byzantine fault-tolerant consensus efficient while ensuring there is no compromise on its security. So I've been talking a lot about Byzantine fault-tolerant consensus. And to explain it, we'll step back 2 decades and we'll look at practical Byzantine fault tolerance protocol. This was the first practical BFT protocol to actually give a practical implementation. And to understand this, we assume a system where there are n replicas. And of these n replicas, only f of them can be Byzantine. And how are n and f related? Basically, n should be greater than or equal to 3f plus 1. And in this example, we consider a scenario where we have 4 replicas. There's primary, there's replica 1, replica 2. And one of the replicas will allow it to be Byzantine. And we have a client. And this client sends this transaction to the primary. Now, primary gets this client transaction. What does the primary do? Well, primary takes the transaction, assigns it some sequence number, and it sends the sequence number as a pre-prepare message to all the other replicas. Now, every replica, when it gets this pre-prepare message, it says, okay, I will believe whatever primary is saying for them now. And what does it do? It basically sends a prepare message in the support of the primary. Now, at this point in time, every replica waits for prepare message from majority of other replicas. In this system, the majority will be 2f plus 1, basically 3 messages. So once a replica gets 3f plus 1 messages, now this replica has a guarantee that, okay, majority of other people have also seen this transaction. So they go ahead and send a commit message in the support. And now again, the same thing happens once a replica gets commit messages from majority of other replicas. It has a broader support. It has a stronger guarantee that this transaction has not only been seen, but many other replicas have prepared this transaction. So they go ahead and execute this transaction. And after executing, everyone sends a reply to the client. Client gets his f plus 1 responses. Client is happy. Client goes home. But what is the problem? The problem is this protocol is very expensive. As you can see, there's a prepare phase and there's a commit phase, which requires n square messages, quadratic communication. And if you're going to design a system with that amount of quadratic communication, it may not be scalable. So there have been a lot of works who have presented exciting solutions to solve this problem. Two of those works are ZZY and SBFT. And these protocols, what they define is something they call as twin path design. There's a fast path where the protocol works nice, it is linear. And as soon as any failure happens, there's a slow path. And that is a problem because failures can simply happen. And the throughput should not just fall because of that. So how do we solve that? And we solve it by our first solution, which we call as proof of execution. Proof of execution protocol was part of the proceedings of EDPT 2021. And what does proof of execution protocol state? First, it is a 3-phase linear protocol. There's no quadratic communication. Second, it allows speculative execution. Third, it allows out of order message processing. There's no sequentialization here. And finally, we allow it to not depend on clients or trusted components. And there's no twin path here. So how does PoE works, basically? For the PoE, we'll use the same system as PBFT. We again have n equal to 4 replicas. At most, one of them could be Byzantine. We again have the same system where there's client and there are 4 replicas. And there's a primary. The client sends this transaction to the primary the same way. And the primary attaches a sequence number and sends it to all the other replicas as a prepare message. So till now, we're exactly the same as PBFT. Nothing has changed. But things will change from now. In PBFT, after this point in time, every replica sends message to everyone else. But we'll not do that. We'll ask every replica to basically create a share, a signed share. And then they send their signed share to the primary. Now, when primary gets this signed share from majority of other replicas, it creates a threshold signature. And it combines them in a threshold signature, and it sends the threshold signatures as a certificate to all other replicas. And finally, when every replica gets this threshold signature, it has a guarantee that this threshold signature could not be made by alone. It needed support of 2f plus 1 other replicas. So these replicas go ahead, they execute the transaction, and then they reply to the client. And that is how PoE works. But PBFT required 3 phases. Then there were quadratic communication. We don't require any quadratic communication. So how did we solve this problem? Where did that extra phase go of quadratic communication? Well, for that, we should look at the magical ingredient of PoE. The thing about PoE is that we allow clients, if a client commits a transaction, it is assumed as final. Basically, if client receives responses from majority of other replicas, then that transaction will persist in time. Whether this primary is replaced or not, irrespective of that transaction will persist. But we allow replicas to roll back if some transaction is not final. Now, all of these protocols, whether it's PBFT, PoE, ZZY, and so on, all of these protocols are basically primary based. Primary is the king. If primary says everyone, let's order transaction, everyone rally behind the primary. What if the primary is Byzantine or primary just stops responding? Then the whole system will halt. And this is a problem because now we need to throw the primary away. And in this whole process of replacing the primary, the whole system's throughput will degrade. So we need a system or a protocol which does not depend on the primary. And for that, we present our democratic solution, which we call as resilient concurrent consensus. And we call it democratic because we give all the replicas the power to be the primary. There's not just one primary, there are many primaries now. And everyone works in parallel. And we say decentralized because there will be always a subset of client replicas which is getting ordered in this protocol. So how does RCC work? Well, RCC assumes that as an input, we want some BFT protocol. So RCC is a meta protocol. Inside RCC, we can run any other protocol. We can run PBFT, we can run POE, we can run any other protocol. And it takes how many instances do you want to run parallel? How many primaries do you want? So let's say I want to have Z primaries and I want to run PBFT. So I run, first step is basically run the Z instances in parallel. Then is that once all these instances are complete, we'll get their transactions. And now we order them into a single global order. And then finally, we execute these transactions. And using this simple idea, we were able to design a protocol which is not in parallel, has high throughput, and allows this democracy. And RCC was part of the proceedings of ICD 2021 and this 2019. So how does RCC work? Well, to understand the working of RCC, we'll take a simple example where we have PBFT and we are running with 2 instances. And we'll see here we have 4 replicas. There's a replica on the top, and there's another second replica, there's a third replica, and 4th replica. And in each replica, there are 2 instances. The instances are tagged as 1 and 2, if you can see. And for each instance, we define some replica as the primary. For instance number 1, we designated the first replica as the primary. For instance number 2, we designated the third replica as the primary. And now what we allow is that each of these instances to be run by the respective primaries and let the consensus flow. The clients are there, and these clients are sending the transaction to their respective instances. The clients don't know about instance, but they know about which replicas to send the transactions. And now these primaries, they will now start the PBFT protocol. All the same stages of PBFT that we have sent. The first stage, pre-prepare phase. Next, prepare phase. And then finally, the commit phase. So exactly what happens in PBFT, that is what is happening. Nothing has changed. Now, at the end of the commit phase, every replica will wait for request that has been ordered by each instance. So in this case, every replica will wait for 2 requests. And once it gets both of these requests, it will create a global order, it will execute those transactions, and it will reply to the client. So that is it. That is how RCC works. But is that also simple? How do we securely order the transactions in this system? It is possible that there might be some Byzantine players in the system who might want to get their transaction ordered before another transaction. Also, now we are saying we want to run so many instances in parallel. What happens if one instance fails? Do we just shut down the whole protocol for that? Finally, how do we guarantee this continuous ordering of requests? And what if multiple of these primaries collude together and do some attack? So for brevity in this presentation, I'll tackle 2 of the challenges and I'll present their solutions. And for the rest of the problems and solutions, I will refer you to the paper. So the first challenge I was talking about is how do we securely order the request? To understand why do we actually need to securely order the request, we need to see some attack. And for that attack, we look at a very simple smart contract. This smart contract is basically transfer ABM. So if balance of A is greater than M, then we remove M from A's balance and we add M to B's balance. That is it. That is what the smart contract is doing. And we'll consider 3 of our players, Alice, Bob, and Eve. And their initial amounts are like $5 in Alice account, 0 for Bob, and 0 for Eve. And we'll consider 2 transactions, T1 and T2. What does T1 do? T1 basically transfers $2 from Alice's account to Bob's account. And T2 basically transfers $1 from Bob's account to Eve's account. And what we want to show in this example is that it actually matters whether we do T1 followed by T2 or T2 followed by T1. So to explain this, we first start by T1, then T2. If I run T1, then the balance changes like this. Alice's balance becomes 3, and Bob's balance becomes 2, and Eve's balance becomes 0. And now if I run T1, Bob's final balance is 1, and Eve's final balance is 1. Let's do the other way around. Let's do T2 followed by T1. So if I do T2 followed by T1, then I'll try to do T1 first. If I do, I do T2 first. And if I do T2 first, Bob's balance is 0. So nothing deducts from Bob's account. And then I do T1, then Bob's account has $2. So if I was Bob and I want to earn profit, I would definitely like the transaction ordering to be T2 followed by T1 because that gives me an extra $1. So what we want a system where the clients do not know how they're ordering the transaction so that they cannot have their bias and they cannot basically collude with malicious replicas. And for that, we present a secure ordering algorithm. Basically, in each round, we require each replica to do the following. Collect requests from all the instances, create a sequence of these requests, hash this sequence, and then call a function fs, which we'll define soon. This function fs is basically a secret ingredient. So what does the fs say that? The sequence remains as it is if it is only of size 1, but in other cases, we basically remove the qth element of the rth stream, and then we append this qth element at the end of the sequence. And how do we define q and r is as follows. Basically, in this function, what we're trying to do is that we're trying to create a permutation of the sequence. You're given one sequence, which is known by everyone. And then if you use this q and r values and you append them in this formula, then you'll be able to create a permutation which is not known to the replicas, clients. Now, another challenge that we talked about is collusion attacks. So this challenge does not happen in single primary protocols. In single primary protocols, there's only one primary. And this one primary, if anything he does bad, he can be removed. But now, as soon as we are allowing many replicas to be primary, so we can allow many Byzantine replicas to be primary. So this will lead to new unprecedented attacks. To explain this, we'll assume 4 sets. There's a set A of F replicas, set B of another F replica, C of set 1 replica, and there is a set M of Byzantine replicas F. Total 3 F plus 1 replicas. So A, B, C are good replicas, M is Byzantine replicas, and there are 2 primaries, P1 and P2, and both of them are Byzantine. So what does P1 do? P1 has a transaction P1, and it sends 2 replicas in set A and C, and obviously to the Byzantine replicas. And what does P2 do? P2 sends a transaction to replicas in B and C, and obviously to malicious replicas. So malicious replicas and M got both the transaction M1 and M2. C also got both the transaction. Both of them, M and C replicas, they go ahead and execute the transaction, reply to the client. But replicas in A, they only got T1. Replicas in B only got T2, and they both are stuck. They cannot order because one of their instances is not responding. And they can shout that, hey, the primary is bad, do something, but nobody will listen because each set has only F replicas. And F is just Byzantine number. You cannot just go ahead and replace on F replicas saying the time to replace the primary. And as a result, the system liveness is in danger. So how do we solve all of these problems? First, we say that if there are some instances that have failed, then what we do is that we only stop them. We do not replace them. And in future, we give them opportunity to come back and start again. And in case there is a collusion attack, we do a little observation that if there are at least F plus 1 replicas who are blaming at least 2 primaries, then there is this collusion attack because there must be F plus 1 distant replicas and they're not blaming 1 prime, they're blaming 2 primaries. So we know that some form of collusion is happening, and we solve it by allowing lightweight checkpoints to run. Now, we have designed POE, we have designed RCC, but we need to actually evaluate these protocols. And to evaluate them, what we use is a ResilientDB framework, which is basically a high throughput permission blockchain fabric. And ResilientDB is open source. It is part of the proceeding of ICDCS and VLDB. And we use this framework to evaluate all of our protocols. You can go ahead, download ResilientDB, you can run it, use it. But why should you use ResilientDB? There are so many systems existing. First, we already know Bitcoin, Ethereum, this initial system, have quite low throughput. So we need a system which can have actually high performance. And then there are many other existing permission blockchains databases systems like Hyperledger, which you can use, but these systems also have quite low throughput. The problem is all of these systems blame the BFT consensus as the problem. They say that BFT consensus is slow, so our systems are not able to actually perform well. But we believe the system design itself is quite overlooked. There are so many practices which can be used to make it performant, and that is what we do in ResilientDB. ResilientDB helps to achieve high throughput. And to illustrate that, we use this very simple example and we ask a very simple question. Can a well-crafted system that uses a slow protocol outperform a system which uses a modern protocol? For example, in this figure, ResilientDB, we make it use PBFT that requires 3 phases and 2 of them are quadratic. And the other system, we make it use ZZY. It's a linear single-phase protocol. And still we see that ResilientDB scales much better than the other protocol. And that is why we believe in ResilientDB to basically run all of our systems in design. But what is beneath ResilientDB? It's basically a layered architecture. There's a network layer to handle all the incoming connections. There's an execution layer to execute all the messages. Now, if you want to have some security, you want to sign some messages, have something, then we have a secure layer. And you want to store data. You want to store your blockchain. You want to secure ledger everything. And then you want to store metadata. We have a storage layer. And more than that, what does Resilient do is that it associates with each replica a multi-threaded deep pipeline. Basically, if you want to see ResilientDB as a black box, every other replica just use it as some black box where the messages are entered. But inside, there's much more happening. There are input threads which are basically taking all the messages. There are batching threads which are basically batching all the client requests to achieve more performance. There's worker thread which is basically managing all the prepare and commit messages. And we have a certified thread for which this manages certificates. Then we have output thread, we basically send messages on the network, and we have an execution thread which basically executes the transaction if required. So that is all happens beneath the skin of ResilientDB. Now, let's try to understand how we evaluated RCC on ResilientDB. So as I said, RCC allows Z instances to run parallel. So we ran 3 experiments. First experiment, RCC with N primaries, which we call RCCN. Another with RCC with F+1 primaries. And finally, we said RCC with just 3 primaries. And we compared it against 4 state-of-the-art protocols. And in this experiment, we scaled RCC from 4 replicas to 91 replicas. And what we saw is that all the 3 variants of RCC are performing much better than all the other protocols. They have higher throughput and they consume lower latencies. Then we thought maybe these protocols are not getting enough batches. What if we increase the size of the batches? Maybe we'll have given larger batches. But still, even after giving them large batches, their performance does not improve that much. What happens in case of RCC? As you can see, the variations of RCC are still performing quite well in comparison to other protocols. So this helps us to prove that not only ResilientDB's design is good, but even RCC as a protocol achieves quite high performance compared to other existing protocols. But what is all happening? What is the big picture here? We have different protocols. All of these protocols are trying to achieve some performance. We have a system which is trying to achieve high performance. The big picture is that we want to basically see blockchain as a service. And that is what we view as the next future work for ourselves. How can we use blockchain as a service? How can we put these protocols and this system in the design? How can we apply blockchain in different applications? And the first thing we thought is one direction is to use trusted computing. So apart from BFT protocols, there are a lot of other protocols that use trusted components in the design. Trusted components like Intel SGX or other. And why they use this thing is to prevent equivocations. Equivocation basically means you can avoid replicas to basically lag. And by using trusted components, these protocols require only 2f+1 replicas. So it seems nice. I mean, the primary cannot lie and only require lesser number of replicas. But the problem is these protocols, our observation has shown, have limited liveness. They require a recovery design and they lack concurrency. And what we vision as our next proposal is a design where we can actually use our existing protocols and our knowledge, and we can use them to make protocols which are safe, live, and concurrent. Next thing, we want to also see in the domain of what is serverless edge. Basically, what is edge computing? A lot of examples of edge computing flow is in Internet of Things. And this edge computing basically uses what we call edge devices. They are 5G devices now. And this edge computing uses these devices to achieve nice performing applications. But the problem is these edge devices have limited computing power and memory. A clear solution would be to how about just use serverless with these edge devices, because serverless is scalable and you do not even require administration. But what is the problem? The problem is that a combination of serverless and edge will be untrusted. Folks at serverless could be Byzantine, they could be Byzantine edge devices. Combining them, how can we get a solution which is Byzantine free? And that is our next vision. Can we make serverless edge combination Byzantine free using our protocols in our system? Finally, our final vision is what if we want to scale all the protocols to the what should I say, invite area networks. And we want to design something which can use any protocol of our all designs. It allows also consensus independently on the system. And between these clusters, there's something happens, low intercost communication. Basically, what we want to have is vision where replicas are divided into some sort of clusters. Each cluster does something, its own consensus using our protocols. And they have somehow able to communicate with each other. And then once they've done the communication, they're able to reply to the clients in order. And that is what we call as where all the replicas need not be in the same place. They can be spread across in a wide area or geoscale locations, and still the consensus would be efficient. So these are basically three of our visions that we see can be used using our current designs to basically help. So to conclude, what we need is basically a decentralized and democratic system. A system where everyone has a right, everyone can work together to reach an agreement. And the first step, what we started was to use commit protocols. And we saw that these existing commit protocols were expensive and some of them were blocking. So what we came up with design of two protocols, which are called easy commit and geoscale easy commit protocols, which alleviated these limitations. But what we realized is that these commit protocols cannot handle Byzantine attacks. They cannot handle message loss. So we moved towards design of efficient BFT protocols. This led us to actually having a study over existing BFT protocols. And existing BFT protocols are again limited. They depend on client, or they have twin paths, or they have quadratic communication. So we designed the first protocol, which we called as PoE, which is linear, uses speculative execution, and supports out-of-order message processing. But we realized PoE also depends on the primary. Primary can do anything it wants, and that leads to reduction in throughput. So we designed a protocol we call it RCC, which is truly democratic. Everyone can become a primary, consensus can happen in parallel, and we can get efficient high throughputs. But finally, we wanted to evaluate all of these protocols something, and for that, we designed a system which we call ResilientDB, which fulfills the dream of having a high throughput permission blockchain fabric. So that concludes my presentation. And before I end this talk, I would like to thank some folks. First, the folks at Explora. I think the first person I should thank is my advisor, who has been an efficient advisor, helps me. Then I should thank my resilient co-authors who have handled me well, Sajid and Yala. And then I should also thank my other co-authors who have worked with me, handled all the load I gave them. So it was nice to work with everyone. They were quite helpful to me. And finally, I should mention a lot of other folks who have been integral part of this thesis, helped me in different stages. And here are just some of them whose name is here. To conclude, there have been several books part of this thesis. Some of these works are there. We also got a chance to write a book where we explain all of our thoughts and different protocols. And then there are different protocols part of this thesis. Thank you.